Hello, Chem 1132. This is Mr. Coker, and getting ready to cover the notes for what we missed on Thursday night. The rest of the notes for Chapter 15, 15.2, and 15.3. I pulled it up here on the screen for the homework. This homework was posted on Tuesday on Canvas, but if you didn't get a chance to see it, here it is. I plan to post the PDF of all these slides so you could, if you want to, print out the ones you don't have yet and take notes on those as I go through them today. All right, so kind of like last week, we had a snow day on a Thursday, so our lab has been postponed to Tuesday. As of now, we're scheduled for, if we don't have another snow day, a test or exam on next Thursday. This will be exam number 2. All right, so without further ado, let's go ahead and get started. I've been talking a lot about equilibrium throughout this period of time. Chapters 12 and 13 and 14 and now 15 all have to do with equilibrium. So we had transitioned from acid-base equilibrium talk to the equilibrium of ionic solids dissolving in water. So the idea, we were talking mainly about solids, and they're having a KSP when they dissolve in water, and that the KSP is the multiplication of the positive and negative ions, each one raised to the power of their coefficient. We only do the product. We only do the what we would consider the top of the equilibrium constant. Excuse me. We only do the product, and we call it the solubility product constant. We do not do the reactant, which is a solid, so we don't include the solid on there. So we started by talking about what if we start with a solid and dissolve it in water. When we reach the solubility limit, then the KSP will equal the concentration of the ions. Another way of looking at this is, what if we come from the other direction? What if we mix ionic solutions together and create a precipitate? So remember, if things have a low solubility, or as we've learned, have a low KSP, a small KSP, when things have low solubility, you can actually mix a solution that contains one of the ions with a solution that contains one of the other ions and generate a precipitate. So that can be analyzed also using KSP values. So in 15.2, we're going to talk about precipitation. Precipitation is a common technique for removing an ion from a mixture of other ions, and also for verifying that that ion is present. If you add the right reagents or chemicals together and get certain precipitates and certain colors and certain textures of precipitates, you can say, okay, I see that that ion was present. And you can analyze qualitatively. So we see here on screen qualitative analysis. You can analyze for simply the presence. You're not trying to measure how much, you're just analyzing that it is there. For example, if you were working in an old home and you were wondering about the paint on the woodwork and whether or not it contained lead, you could take a sample of that paint, dissolve it, add a certain chemical to it, and if you turned a certain color or created a certain precipitate, you would say there is lead in the paint on this woodwork. In fact, they sell those kits at Lowe's and Menards to allow you to test for lead in paint in your home, in an older home. So that is an example of qualitative analysis. In a large scale, qualitative analysis may mean starting with a mixture that may or may not contain very large number of ions, 10, 15, maybe 20 ions, and you could go through a series of steps experimental steps to separate those ions from each other and then test for their presence in the solution. And that would be a qualitative analysis scheme that you might do to analyze a particular solution for the presence of certain metal ions, for instance. So 15.2 is going to talk about forming precipitates and then maybe using those precipitates to analyze a mixture of ions, qualitative analysis. So let's remind ourselves it's mx yields m plus x minus, or maybe mx2 yields m plus 2x minus, or something like that would be the reactions that we're talking about. If you look at it in the reverse direction, m plus x minus yields mx, then that is actually the direction we would say would be the precipitation direction. The forward direction of the reaction is dissolving, but the reverse direction is precipitation. We're going to call the product of m plus times x minus, or whatever is the appropriate combination of the cation and anion multiplying their molarities together, we're going to call that Q, or the reaction quotient, for the ion product. Or we could call it QSP. Makes me think about the old breakfast cereal Quisp. QSP. QSP would be if I used initial concentrations of m plus and x minus to analyze whether or not a precipitate formed, I could use QSP. Remember, using equilibrium concentrations of m plus and x minus would get me KSP. So just like before, you can analyze the number for the equilibrium expression even if you're not at equilibrium. If you're not at equilibrium, we call it Q. And we can say, okay, Q is greater or less than K, and that can help us know which way the equilibrium will shift. In this particular equilibrium for dissolving and crystallizing, or dissolving and forming solid, the forward direction, if it shifts to the right, then we're going to dissolve more solid. If it shifts to the left, we're going to form the solid, which would be forming a precipitate. So the value of QSP is you can use QSP and compare it to KSP to predict whether or not a precipitate will occur when you mix certain initial concentrations of ions together. So the general analysis will be, if your QSP is greater than your KSP, it means that these ions concentrations are above the solubility limit, and they will correct by forming solid and bringing those ion concentrations down to the solubility limit. So if QSP is greater than KSP, we would expect this equilibrium to shift to the left. We would expect solid to form. And enough solid will form to bring the m plus and x minus back down to a number where they now equal KSP. So not all of m plus and x minus will crystallize out as solid or form a precipitate, but enough will do that to get you back to KSP for that product of m plus times x minus. Now, if your QSP is calculated and it's lower than KSP, it means that m plus and x minus do not have a high enough concentration to be considered at the solubility limit. And so we would have no precipitation occurring in that particular case. In fact, if solid were added to that mixture, or if solid were in that mixture, we would expect solid to dissolve until it reaches the concentrations for the ions that allows it to equal KSP. So this is our general analysis, is to calculate what is the product of the product ions, calculate that value. What is that mathematical value, and then compare it to the KSP for that particular ionic solid. And if it's greater, it will precipitate. If it's less than, it will not. So let's do an example of this. A solution is prepared by adding 750 milliliters of 4 times 10 to the minus 3 molar cerium 3 nitrate. So I would not worry about the nitrate on this particular example because nitrates we know have very high solubilities, but the cerium plus 3 ion might form a precipitate with the negative ion from the second half of the mixture. The second half of the mixture is we're going to add to this cerium nitrate 300 milliliters of 2 times 10 to the minus 2 molar KiO3. So the K plus part of this, the potassium ion, that's probably not the precipitate because we know that alkali metals tend to always be very soluble. But the iodate, the IO3 minus, might combine with the Ce plus 3 to make a precipitate. So our question is this particular mixture with these amounts and these molarities going to generate a precipitate of cerium 3 iodate, CeIO3 taken 3 times, will CeIO33 with a KSP of 1.9 times 10 minus 10 precipitate from this solution. Now, one might just look at the concentrations of KiO3 and cerium nitrate and just start multiplying them together to get your QSP. However, you would be overlooking the fact that adding 750 milliliters to the other 300 milliliters, both of these solutions are going to change each other's molarities by mixing. Because adding the 300 milliliters to the 750 is akin or similar to adding water to the cerium nitrate. You've got 750 milliliters and its molarity is 4 times 10 minus 3. But by adding this second solution to it, you are in fact diluting it. And you're diluting the 300 milliliters of 2 times 10 minus 2 molar KiO3 with the 750 milliliters of solution that you're adding of cerium nitrate. And so they are mutually diluting each other. So one of the first things to worry about when you or to calculate when you do this is you have to first calculate how much cerium plus 3 molarity is in the solution after the mixing. So that reminds us to go back to our molarity 1, volume 1 equals molarity 2, volume 2, the dilution equation. Because the cerium ion will be diluted by the potassium iodate solution, and the iodate ion in the KiO3 solution will be diluted by the cerium plus 3. Now, instead of converting milliliters to liters and multiplying by molarity, we're going to do this in millimoles and milliliters. So 4 times 10 to the minus 3 moles per liter is the same as 4 times 10 to the minus 3 millimoles per milliliter. So 750 milliliters times 4 times 10 to the minus 3, that's M1 times V1 for the cerium plus 3, divided by V2, which is the 750 plus the 300 that you're adding to it from the KiO3 solution. So 750 times 4 times 10 minus 3 divided by 1050 means that after mixing, the cerium plus 3 has a molarity now diluted down to 2.86 times 10 minus 3. Doing a similar calculation with the iodate, IO3 minus, it had 300 milliliters and 2 times 10 minus 2 millimoles per milliliter divided by 1050, which is the new volume once you add the 750 to the 300. So it's M1 V1 divided by V2 gets our new molarity after dilution for iodate to be 5.71 times 10 minus 3. So keep in mind, if you're doing one of these problems, determining whether a precipitate occurs, you have to account for the dilution effect from mixing the two solutions. When you mix two solutions, they dilute each other and change each other's molarities. Okay, with these two new molarities calculated, we now have initial molarities, so we could solve for QSP. So the ion product, or QSP, for cerium iodate CeIO33 is the cerium ion plus 3 times the iodate ion cubed, because there are 3 of that ion When you separate CeIO33 out, I didn't write out the balanced equation, but you would see that you're going to get one cerium plus 3, and you're going to get 3 IO3 minuses. So since that coefficient is 3, we have to move it to the exponent. So this calculates on our calculators to be 2.86 times 10 minus 3 times 5.71 times 10 minus third quantity squared, and that comes out to 5.32 times 10 to the minus 10. Now comparing that to the KSP, which was only 1.9 times 10 to the minus 10, it appears that we are going to be higher than the K value, which means these ions have too high of a concentration to equal KSP. They are over the solubility limit, and to correct, they will precipitate from the solution as CeIO33 until they bring their numbers down for aqueous ions in solution to 1.9 times 10 minus 10 for this calculation. So that's how you do these precipitate problems. You first account for the dilution and find the molarities of your positive ion and your negative ion, your cation and anion. Then plug them into the expression of the ions multiplied together, and then compare the value you get for your reaction quotient Q to your KSP number to see if it's bigger or smaller. If it's bigger, you expect a precipitate to occur. Okay, so another quick example. This one's going to go a step farther, or further rather, in asking you to calculate what concentrations of magnesium plus 2 and F minus you're going to have after the precipitate forms. So instead of just saying, will a precipitate form, we're also going to do the stoichiometry to determine how much of each ion is present after the precipitation occurs. So we're adding an extra step to it. But first, we have to do our dilution. So looking at the milliliters and molarities for the magnesium ion and the milliliters and molarities for the fluoride ion, because it's MgF2 that we're concerned about here. I'm not concerned about the sodium nitrate precipitating because nitrates and alkali metals are always soluble. So it's MgF2 that we're concerned about here. We need to find the Mg plus 2 ions molarity after diluting with the other solution, the NaF, and likewise we need to find the F minus's molarity after dilution. So we do the M1 V1 over V2 calculation on this. 150 times 1 times 10 minus 2 for the magnesium plus 2 divided by 400, which is the sum of 150 plus 250. 150 plus 250 is 400. So the two solutions add up to a new volume of 400. And you get 3.75 times 10 minus 3 molar. For the F minus, it's the milliliters of the sodium fluoride times the molarity of the sodium fluoride divided by the final volume after mixing, and you get 6.25 times 10 minus 2. So to verify that we will get some precipitate, we plug these into the Q value, 3.75 times 10 minus 3 times 6.25 times 10 minus 2 squared, and we get 1.46 times 10 minus 5. So that is in fact 10 minus 5 larger than 6.49 times 6.4 times 10 minus 9. So we can verify, since Q is greater than K, solid magnesium fluoride will form. So recognizing that it's going to form, our first step is to assume that it goes all the way to completion. In other words, let's determine which one of these two ions, magnesium plus 2 and F minus, is actually the limiting reactant. So if we take the milliliters times the molarities, we find out that the magnesium plus 2 is actually 1.5 millimoles, and the F minus is 25 millimoles. So we can see that we have a large excess of F minus. Even though it takes two of them, 1.5 times 2 would be 3 millimoles, and 25 is a lot bigger than that. So our initial calculation here is to run the reaction all the way to the right, which means the magnesium plus 2, the limiting reactant, is going to go all the way to 0. It's going to use up all the magnesium plus 2 with that large excess of F minus. So the Mg plus 2 is going to go to 0 after the reaction, and the F minus is going to be dropped from 25 down to 22. 25 minus 2 times 1.5. So our F minus is now at 22 millimoles, and our Mg plus 2 is at 0 millimoles. Now, plugging that back in to find the molarity of F minus, the leftover F minus in solution is going to be 22 divided by 400. 22 millimoles divided by 400 milliliters, which is same as 22 moles divided by 400 liters, or 5.50 times 10 to the minus 2 will be the molarity of F minus. Now we did assume that the magnesium went all the way to 0, but we actually know it can't be 0 because then the magnesium times the F minus squared won't equal KSP. So we're actually going to assume that this 5.50 times 10 to the minus 2 molarity F minus is constant. Granted, there will be a minus 2x when it shifts to the right to reach equilibrium, but that minus 2x will be negligible. So what we're going to do is we're going to take the KSP, 6.4 times 10 minus 9, make the Mg plus 2 our unknown, and plug in for F minus this leftover F minus we have from running the reaction to completion, 5.50 times 10 minus 2. So in effect, what we're doing here is we are going all the way right and using up all the magnesium, and then we are letting it come back to equilibrium by running the MgF2 solid makes Mg plus 2F minus reaction. So initially our Mg plus 2 is 0, our F minus is 5.5 times 10 minus 2, but because of the shift to reach equilibrium, the Mg plus 2 will be plus x, and the F minus will be plus 2x. But we're going to consider that plus 2x negligible, plug x in for magnesium plus 2, and 5.5 times 10 minus 2 in for the F minus, solve for the Mg plus 2 by dividing 6.4 times 10 minus 9 by 5.50 times 10 minus 2 quantity squared. And we're going to get that the Mg plus 2 at equilibrium will be 2.1 times 10 to the minus 6. So looking at that compared to the 5.50 times 10 minus 2, it is in fact a negligible amount. And we don't really need that plus 2x on the F minus. Okay, so for that one, we added the extra step at the end. First, we did our calculations. We determined that a precipitate would form, and then to find out how much of each ion from the precipitate would be present at equilibrium, we had to first run the reaction to use up the limiting reactant, and then take the molarity of the F minus and use it to calculate the molarity of Mg plus 2 at equilibrium. Now, taking advantage of the fact that different ions, positive ions, will have different KSPs and different solubilities with the same negative ion, you can actually strategically use the addition of something like sodium chloride or sodium carbonate or something like that with a metal ion like sodium that's soluble. The chloride might form precipitates with one, but not another ion in solution. So you can in fact separate a mixture of two or more positive cations in solution using a technique called selective precipitation. So we can use what negative ion we add to selectively choose to separate one ion as precipitate while leaving the other ion still dissolved. And that's because different metal ions have different solubilities with a particular negative anion. So the addition of a reactant or reagent whose anion is going to form a precipitate with one or more of the metal ions in the mixture, but not all of them, is a technique used in qualitative analysis for separating mixtures out so you can kind of deal with a certain set of ions and separate them away from other ions that may form competing reactions on down the scheme as you go along. So, for example, if you had a solution that had barium plus 2 and silver plus 1, and you added sodium chloride to it, the chloride from the sodium chloride is insoluble with silver. In other words, silver chloride has a very small KSP. But the barium plus 2 ion with chloride is quite soluble. It has a large KSP. So what you could do is you could add an excess of sodium chloride solution to this mixture of barium plus 2 and silver plus 1, and you'd expect that virtually all of your silver plus 1 ions would form solid and sink to the bottom of the test tube or the container, and that the barium plus 2 ions would remain in solution because they are soluble. So then it's just a matter of draining the liquid off the top, which we call, if you're pouring it out, we call that decanting, or you could use a pipette to draw the liquid off. Sometimes we put the test tube in a centrifuge and spin it real fast in order to force the solid out of the mixture and down to the bottom of the test tube so it's nice and tightly packed at the bottom of the test tube. But generally what you do is you add an excess of this reactant that's going to precipitate certain metals, and you get those metals concentrated on the bottom of the test tube as a solid, and then you can pour the liquid off the top or pull the liquid off the top with a pipette and put it in a separate container, and now your barium is in solution in a different test tube and your silver ion is in the silver chloride precipitate in the first test tube. And so in that way, you've separated silver ions from barium ions in solution. So it's a separation technique. And often separation techniques are needed in order to then do further tests in order to verify the presence of certain ions in solution. So let's say we had a solution that was 1 times 10 minus 4 molar copper plus 1 and 2 times 10 minus 3 molar lead plus 2. If we added iodide to that solution, would we see lead 2 iodide precipitating first, or would the copper 1 iodide precipitate first? The lead 2 iodide has a KSP of 1.4 times 10 minus 8. The copper 1 iodide has a KSP of 5.3 times 10 minus 12. So which one is going to precipitate first? Well, the way we would do that is we would say, okay, what concentration of I minus is needed to precipitate copper plus 1, and what concentration of I minus is needed to precipitate the lead plus 2. So that would give us an understanding of which one is going to precipitate first, because as we add the I minus to the solution gradually, one or the other is going to start precipitating first, and so it would be the one that precipitates at the lower concentration of I minus. So looking at PbI2, the KSP is 1.4 times 10 minus 8, which is the lead plus 2 ions molarity times the I minus molarity. So if we know our lead plus 2 in the solution is 2 times 10 minus 3, we can divide both sides by that and then take the square root and get that the I minus is that will start precipitating. In other words, we will start precipitating at an I minus concentration of 2.6 times 10 minus 3. So anything beyond 2.6 times 10 minus 3 molar for I minus will begin pulling lead out of the solution as PbI2. Now doing the same calculation for the CuI, the copper 1 iodide, 5.3 times 10 minus 12, the copper is 1 times 10 minus 4. The iodide would need to be 5.3 times 10 minus 8 in order to start precipitating. So 5.3 times 10 minus 8 is a lot smaller than 2.6 times 10 minus 3. That's like 5 powers of 10 different. So this would tell us that as we slowly, gradually add I minus to the solution, it's the copper ion that's going to precipitate first, leaving the lead ion in solution. So you could carefully add the I minus to the solution, precipitate the copper 1 iodide out, and leave the lead plus 2 in the mixture. And once you form the precipitate, you could then pour off the solution and you'd have your lead plus 2 separated from your copper. So an example of just like a small scheme of separating ions out, taking advantage of different values of KSP. This would be how you would separate copper plus 2, mercury plus 2, nickel plus 2, and manganese plus 2. So let's say you have these 4 ions and you want to separate them into 2 categories or 2 groups. You want to get your copper and your mercury separated out from your manganese and your nickel. What you can do is you can add the molecule hydrogen sulfide, H2S. So H2S would be acidic. It would have a pH around 2 because H2S is going to break up into H plus and HS minus, and then the HS minus is going to break up into H plus and S minus 2. It's a diprotic double acid. H2S has 2 H's, and you're going to end up with some H pluses and some HS minuses and some S minus 2's. Now the S minus 2's are going to be high enough molarity if you've added enough H2S to begin precipitating your copper 2 and your mercury 2, because they precipitate at very low concentrations of S minus 2. And so if you add the right amount of the H2S, you will solidify out all of your copper and silver, or mercury rather, mercury and copper, but leave in solution the manganese plus 2 and the nickel plus 2. Now, if you drain that solution off that has the manganese and the nickel in it, and then you add some base to that, the base is going to convert more of your H2S and your HS minus to S minus 2. So the base, because it reacts with H plus on the right side of the equilibrium for H2S, it's going to pull the equilibrium to the right, generating more of that S minus 2 ion. Now that's going to bring those S minus 2 ions up to a high enough concentration to now precipitate the manganese and the nickel. Just by changing the pH, you are increasing the S minus 2 ion concentration. So at the low S minus 2 concentrations for an acidic solution, it's still enough S minus 2 to precipitate the copper and the mercury. But once they are out of the solution and you've poured off the liquid, you then could bring the pH up with hydroxide to around a pH of 8, and you would begin precipitating your manganese and your nickel. And so you're separating those 4 ions out of solution because of their tendencies to form precipitates with S minus 2. So qualitative analysis, which I've alluded to up till now, is analyzing a mixture that contains various cations, or sometimes we can do qualitative analysis even on anions, but for this particular discussion, we're going to talk about cations, or metal positive ions. So qualitative analysis would be identifying the presence of certain chemical species in a mixture. So for instance, do I have calcium ion in this mixture? Do I have copper plus 2 ion in this mixture? Do I have mercury plus 2 ion in this mixture? And one way to look at that is to look at selective precipitation procedures that will separate your ions out from each other, so you can then use certain additional chemicals to verify the existence of those ions in the solution. So for the purpose of this, we typically separate our cations into 5 categories, with group 1 being the cations that are insoluble with chloride. So, we saw that silver was one of those that's insoluble with chloride. Group 2 is going to be our sulfides, and those would be things like copper and mercury, which are insoluble in acid solution with sulfide. And then remember, your manganese and your nickel from the previous slide are sulfides that are insoluble in basic solution. We'll call those group 3. So with just chloride and sulfide, you can get 3 of the groups separated out by just manipulating the pH to get group 2 and group 3 separated out. Group 4, you're going to have to precipitate with carbonate. And then group 5 are the ones that are always soluble, which are your alkali metals and your ammonium ions. For that, you may need to do something as wild as putting it in a flame test and seeing if you get the color of a certain alkali metal or something like that. So separating a set of solution with a set of ions in it into these 5 groups is obviously not the end of the process. After separating them into these 5 groups, you would then use some more reactants and reagents to then separate those groups into subgroups. For example, there may be 3 or 4 ions in group 1. How do you now know which of the 3 or 4 ions you have? You may need to do some more chemistry on that and identify your individual ions looking at the specific chemistry of each cation. So this would be how you would start with a large set of ions. How many do we have here? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. 26 ions. 26 positive cations. And if you follow this particular set of additions of solutions that you would, or reactants or reagents, I guess we would call them, reagents that you would add to this mixture, and you do it by selective precipitation, you can in fact separate these 26 into the 5 basic groups. Once you get them down to the 5 basic groups, you could do some other steps to separate them further into figure out which of the individual metals you have. So to start with, to get your group 1 to precipitate, you would add HCl, because the Cl- will precipitate the silver chloride, the mercury 1 chloride, and the lead 2 chloride. And then you pour off the solution, and that's going to have your group 2 through 5 in it. If you add H2S with a low pH, you're going to get your acid insoluble sulfides, your group 2s. That would be the copper 2, the bismuth, the cadmium, the lead, the mercury 2, the arsenic, and the antimony, and the tin. Those would all be jumbled together as a mixed up precipitate at the bottom of the test tube, and then the liquid you would pour off would be the group 3s through 3s, 4s, and 5s. Then if you raise the pH to about 8 using NaOH, sodium hydroxide, your group 3 is going to precipitate. Remember, that contained the manganese and the nickel, but it'll also have the aluminum and the iron and the chromium. Some of them are going to precipitate as hydroxides. Some of them are going to precipitate as sulfides. So for some of these, it's the sulfide ions molarity going up with the addition of the base, but for others, they might even be precipitated just from the hydroxide being added. And so that would be your group 3 precipitates. Then all you have left is your group 4s and 5s, and to that liquid you would add some sodium carbonate, which would then precipitate out your barium carbonate, your calcium carbonate, and your magnesium carbonate, but your sodiums and potassiums and lithiums and ammoniums and those would still be soluble, and they would remain in solution. So you see by a strategic flow chart here, you could, and you have to, of course, keep track of what you have in each test tube, but you could take a complex set of 26 ions and in 5 different groups and separate those 5 different groups into 5 different test tubes using selective precipitation. All right, so now we have one more kind of equilibria. This is an equilibria that actually typically lies far to the right. We've been doing equilibria with small k's for quite a while now, but these are equilibria that are going to get you reactions that lie far to the right. And these involve complex ions, which are combinations of molecules and ions sticking together in solution. So a complex ion is when you have a metal ion and then it's surrounded by molecules or other ions to create a charged combination. So you have these charged species consisting of a metal ion surrounded by various ligands. We call the things that are sticking to the metal ion ligands, L-I-G-A-N-D. So there's a new vocabulary word. Ligands always have one thing in common. They're always Lewis bases. So remember, a Lewis base is a molecule or an ion that has electron pairs that can be donated to make a bond. So your metal ion is going to have these empty orbitals that can then accept the pair of electrons from the ligand to make a covalent bond between the ligand and the metal ion. So we see this in water when water attaches to metal ions to form hydrated spheres around metal ions. That's an example of water being a ligand and the metal ion bonding to the water using empty orbitals. So some common ligands would be water. Ammonia has an unbonded pair of electrons, a lone pair of electrons. Chloride makes a good ligand. Cyanide is also a good ligand. These ligands surround these ions, sometimes in pairs, sometimes in groups of 4, sometimes in groups of 6. They're usually even numbers for your number of ligands that will attach to a certain metal ion. And we call the number of ligands that are attaching, we call it the coordination number. So if 6 ammonias surround a copper ion to make CuNH3 6 plus 2, we would say in this case that the coordination number is 6 because there are 6 ammonia ligands surrounding the copper plus 2. The copper and chloride typically forms a set of 4 in a tetrahedral pattern, and that would be a coordination of 4. Nickel cyanide also can do a coordination number of 4. Copper 2 chloride, CuCl2, can do it in a group of 2. With copper plus 1 in the center and 2 Cl minuses, you get an overall charge of -1 with a coordination number of 2. So remember, these are always charged species. They're always positive or negative ions in the water, but you have these ligands attaching to these metal ions. The equilibrium constant is actually called a formation constant. Some people call it a stability constant. And that would be the equilibrium constant for each step of forming the complex ion. So each additional ligand is a different step. So it's kind of like a multiple hydrogen or polyprotic acid breaking up step by step to make H plus and negative ions. This is, you start with the metal ion and then you add one ligand and that has a K number, and then you add another ligand and that has a K number until you get to your coordination number. So you may actually have 6 steps if you've got a coordination number of 6 to this, and each one has its own equilibrium constant. Let's try to keep it simple and just go with a coordination number of 2. Silver plus 1 can make complex ion with thiosulfate S2O3 minus 2. And if one S2O3 minus 2 adds to it, you get AgS2O3. When the second adds to it, which has a minus 1 charge, when the second adds to it, you get AgS2O3 taken twice, 3 minus. And so we are going to mix some sodium thiosulfate with some silver nitrate and try to form these complex ions. So the K for the first formation constant of the complex ion is the silver plus the thiosulfate makes AgS2O3 minus, and that has a K1 of 7.4 times 10 to the 8th. So I told you these have large K numbers, large equilibrium constants. And then for the second addition of the ligand S2O3 minus 2, the formation constant is 3.9 times 10 to the 4th. Once again, large K. So to get the concentrations of these ions, we have to do that thing where we take the milliliters times the molarity and divide by the total volume of the solution, because the 150 milliliters of the silver nitrate is going to dilute the 200 milliliters of the sodium thiosulfate. So to get their initial molarities before forming the complex ions, we have to do the M1 V1 over V2 to get the molarities. And here our calculations are that silver plus 1 is 4.29 times 10 minus 4, and the thiosulfate is 2.86. Now, since this thiosulfate is so much larger than the silver, and the fact that the Ks are large, we can treat this as stoichiometry. When you have a large K, you can assume the reaction goes far to the right. You can assume it's just like stoichiometry. So what we're going to assume here is that the reactions go all the way to completion using up all of our silver, with the S2O3 2 minus being left over as excess. So before the reaction, the silver plus 1 is 4.29 times 10 minus 4, and the S2O3 2 minus is 2.86. After the reaction, the silver is going to get down to 0. The S2O3 minus 2 is going to be still about 2.86 because the amount you subtract from it is negligible according to sig figs. And then our silver attached to two thiosulfates complex ion, that's now going to have a molarity of 4.29 times 10 minus 4. So what we're doing here is K's are large. We're going to react both steps all the way to the right. So we're actually writing it as combination of the two steps, Ag plus 2, S2O3 minus 2, making the silver with the two thiosulfates on it. The silver plus 1 is limiting, so, and the amount of thiosulfate used up is negligible. So we're just doing this by stoichiometry. We're just taking the limiting reactant, running it down to 0, and then seeing how much product we make. But we can't assume that the silver plus 1 ion is going to be actually 0 at equilibrium. And so what we do is we start with the second equilibrium. 3.9 times 10 to the 4th is the K2 for the second step of the formation of the complex ion. And we plug in the molarity of the complex ion with the two thiosulfates, and we plug in the 2.86 for the thiosulfate, and we solve for how much silver S2O3 minus 1 with only one thiosulfate on it we have, and we get that we have 3.8 times 10 minus 9 moles per liter of the silver with only one ligand attached. And then we put that back in the first K formation constant reaction. Remember, the first K1 was 7.4 times 10 to the 8th. We put our 3.8 times 10 minus 9 number in for that, and the S2O3 minus 2 number 2.86 for that, and we use that to solve for the silver ion, and the silver ion, which is virtually 0, is in fact 1.8 times 10 minus 18. So it's not in fact 0, it's just close to 0. So through a series of first doing stoichiometry and then doing the equilibrium constants, we've solved for how much of each ion is present. We solve for the silver with the 2 thiosulfates on it. We solve for the silver with the 1 thiosulfate on it. We solve for the silver without any thiosulfates on it. And we find out that very, very little of the silver is not attached to thiosulfate. This can actually be used to dissolve something that's insoluble in as an ionic solid. For example, if you've got some silver chloride and you want to dissolve it, what you can do is you can get your silvers to dissolve by adding the thiosulfate to it, for instance. So this in fact gives us a second strategy for dissolving something that's normally insoluble in water. Remember, our first strategy was from our acid-base chapter, or actually 15.1, I think, for KSP. For 15.1, remember back in 15.1 we talked about that if your anion from your solid is a good base, you can actually dissolve it by acidifying the solution. But in cases where the anion is not basic, what you can do is you can actually add ligands that will form a stable complex ion with the cation. And that will remove the cation from the right side of the equation, shifting the equilibrium to the right and making it more soluble. So, 2 ways to get something that's normally water insoluble to dissolve. One is adjust the pH, and maybe you can get that anion to go into solution, and that will pull the equilibrium to the right. Or the other one is to add a ligand, like we saw with the thiosulfate and the silver ion, and that will actually get the cation out of solution, which will then pull the equilibrium to the right and make it more soluble. So let's talk about one of those qualitative analysis schemes and what we might do to group 1. Now we could go into the same discussion with group 2 and 3 and 4 and 5, but we're just kind of giving you a taste of qualitative analysis here by showing you what you could do to that precipitate if you have your group 1 ions separated out from the other ions. So let's say, for instance, that you had your mixture of 26 ions and you added some hydrochloric acid to it, and you got your silver chloride, your mercury 1 chloride, and your lead 2 chloride separated out. Remember, that was this first step, where you add the HCl and group 1 comes out in the purple box as insoluble chlorides. Now, if you've got those as a solid and you separate them out, what could you then do to further separate the silver chloride and the mercury chloride and the lead chloride into 3 different test tubes in order to test for their existence? Well, the first thing you could do is you could simply warm the test tube. You just pass the test tube over a Bunsen burner, and with a little bit of warmth, you'll find that your lead chloride redissolves. Lead chloride dissolving in water is very temperature sensitive, and you could actually get your silver chloride and mercury chloride stay dissolved. If you just slightly warm the solution, you'll get your lead chloride to dissolve. And so you might add a little water to the precipitate, warm it a little bit, and then pour off the water, and the water you pour off should have lead plus 2 in it. And then if you want to see if it does, you simply add some sodium chromate to it, CrO42 minus ion, and if it turns yellow, that's a positive test for lead. So you'd separate out your 3 ions into chlorides. You'd have the liquid poured off that had all the other groups in it. You'd have only your group 1 ions, your silver chloride, your mercury, and your lead. You would add a little water to it and heat it, pour the water off, decant the water off, and then add chromate to that. And if it turns yellow, yes, you have lead. Now you poured off the water, but what was left in the test tube was a solid that contained silver chloride and mercury chloride because they were not soluble even by warming. So now we can take advantage of the formation of complex ions. We could add some ammonia to our silver chloride and our mercury chloride because ammonia forms a complex ion with silver. So that would get your silver chloride to dissolve because you would get the silver ion making this complex ion with the ammonia. So by adding ammonia to silver chloride, you can redissolve the silver into solution as the silver 2 coordination number with ammonia ion. And then by adding H+, you convert your ammonia back to ammonium. So you add a little bit of acid to that liquid that you've poured off. And if the white precipitate reforms, that means you had the silver chloride in it. So you're going to basically get rid of that formation, complex ion. You're going to get rid of that complex ion by acidifying the solution and converting the ammonias into ammoniums. Because when you have ammonia in the form of ammonium, it doesn't have an unshared pair to bond with the silver anymore. The addition of the ammonia, if it forms a black and white precipitate, that is in fact a positive test for the mercury. So the addition of the ammonia solution, your precipitate would change colors to black and white, and that would tell you that you have ammonia. You pour off the liquid, and the ammonia would be the silver ion with it, and the liquid would then be acidified or add H+ to see if it turns white again. So by going through these steps and practicing and knowing what to look for, you could in fact take the group 1 ions and verify, do I have lead, do I have silver, and do I have mercury? So these are qualitative analysis schemes, but you don't do them without practice. You practice them and practice them and practice them until you're good at recognizing the different precipitates and how much to add and how much to heat and so forth. It's almost an art form. You know, it's kind of like the first time you paint a painting with oil paints on a canvas. You know, maybe it doesn't come out too well, and you make some mistakes. But then the more you practice it, so it's qualitative analysis is a bit of an art form, and some people are very practiced at it and very good at doing all the steps and mixing the things together in the right proportions to verify the presence of different ions. Now we've only done the scheme for group 1, so there would be a similar scheme for the group 2 ions that you had separated out, and the group 3 ions that you separate out, in order to separate those further into different containers and then test for the presence of the different ions. Let's do a calculation here of what the solubility of silver chloride would be in 10 molar ammonia. Remember back here we were adding ammonia to get the silver chloride to dissolve. So let's look at the solubility of silver chloride if we have 10 molar ammonia, which is concentrated ammonia, that we've added to a precipitate of silver chloride, just to see how concentrated, how much silver chloride can we get to dissolve if we add 10 molar ammonia. So the first formation constant for silver ion with ammonia is 2.1 times 10 to the third. The second formation constant for adding a second ammonia to make the complex ion AgNH32 plus 1 is 8.2 times 10 to the third. The dissolving of silver chloride in water has a KSP of 1.6 times 10 to the minus 10. Now, if we look at these three reactions added together, you cancel out the Ag pluses, cancel out the AgNH3 pluses, cancel out nothing else actually cancels out. You get AgCl solid plus 2NH3 has an equilibrium with AgNH3 2 plus Cl minus. This is actually the equilibrium we're interested in analyzing because we are trying to find out how the ammonia dissolves the silver chloride to make the complex ion and the chloride. Now remember, if these three reactions add together to get this equilibrium, then we multiply their K values. So we would take the 2.1 times 10 to the third, the 8.2 times 10 to the third, and the 1.6 times 10 minus 10, and we'd get a K value of 2.8 times 10 minus 3. And now we set it up as an ice table. So our initial, we don't care about our initial concentration of AgCl solid because it's a solid. Our initial molarity of ammonia is 10. We don't have any of the complex ion yet, and none of our chloride has dissolved yet at the start of the reaction. But then as it shifts to the right, it's going to be minus 2x, plus x, and plus x. So the equilibrium is going to be 10 minus 2x, x, and x. So then we end up with 2.8 times 10 minus 3, the K for the reaction, equal to x times x divided by 10 minus 2x quantities squared. Now you might think we could drop the minus 2x, but actually we don't need to because this one can use the shortcut of taking the square root of both sides to get rid of the quadratic equation. And when you do that and work out the algebra, and I didn't show all the work for the algebra, but when you do that and work out all the algebra, take square root of both sides and solve for x, you get x equal 0.48 molar, which is actually a fairly high concentration. It's almost half of a mole per liter of silver chloride, something that's normally very insoluble, but fairly soluble in 10 molar ammonia. So 0.48 molar would be X. That would be the Cl minus ion that would dissolve, meaning that's how much AgCl you got to dissolve. The Ag would be in the form of AgNH3 2 plus. Now how much ammonia is left over? Well, looking at 10 minus 2x, that would be 10 minus 0.96, which comes out to one decimal place to be 9.0. 9.04, I think, molarity. Okay, so that is the notes. I'm going to post these to Canvas, or actually I'm going to post these on, I'm going to post this video on YouTube, and then I'll post the link to that, plus these notes, plus the quiz on Canvas for you and send that out as an announcement sometime this morning. So thank you for your patience as I tried to pull all this together and get this out to you.